Ladies and gentlemen, I'm going to talk about optoelectronics, what that field is, and what are the challenges and current directions in this field. So first, a couple of slides. What is optoelectronics? Then how material science is affecting actually very much optoelectronic research. Then several applications. Optoelectronic devices appear in many places in people's lives nowadays. And finally, I will show a couple of examples of where our current research is going and how nanotechnology is related to this. So in optoelectronics, we have to go a little bit into physics. There are three processes by which light and matter interact. And here we have absorption. So as you know, light is consisting of photons, quanta of light. So photon can be absorbed and to produce excited electrons. Then electrons can emit light by either spontaneous emission without the action of another photon, or it can produce photon stimulated or induced by another photon. And these photons have same phase and same energy. And optoelectronic devices either convert electrical energy to optical energy by these two last processes, or optical energy to electrical like in the first process. And the devices that are based on these three phenomena, LEDs, are based on spontaneous emission of light. Lasers are based on the stimulated emission process, and it only differs by introduction of mirrors so that light is amplified. And then we have detectors and solar cells, very large group of applications there, which are based on absorption. So that is optoelectronics. And next, how this material science is affecting optoelectronics. In optoelectronics, we mainly use 3,5 semiconductors. So it means that there are elements from group 3 in this table of elements, and then group 5. So these have an average valence of 4, which is the same as in silicon. Most of the electronic circuits are based on silicon, but as the silicon is not a very good light emitter, we have to use other options in optoelectronics. So there are a lot of different compounds that you can form from these chemical elements, and you can also alloy them. So you can mix these binary compounds to more complicated materials. And these materials typically crystallize in zinc blende or word-side lattice. Here is a picture of the zinc blende lattice, where there are two different kinds of atoms. So the group 3 and group 5 atoms have their own places in this lattice. And this ordering forms energy bands, so that we have clearly defined energies which can interact with the light. And we can also dope these materials to change their conductivity. And this is very important table in optoelectronics figure. This shows different 3,5 and 2,6 materials, and what are their either lattice constant, so coming from the crystal structure, and the band gap energy coming from the energy structure. And this is compared to the solar spectrum on the right. And those colors, green and blue, define 3,5 compounds, and as we can see, there are actually very little 3,5 compounds in the visible area. They are more concentrated on the infrared spectrum, but also the sun's spectrum is concentrated mostly there. So for visible light applications, the best materials group is nitrides. Materials based on gallium nitride, indium nitride cover the whole visible spectrum. And how we make these materials? We make these by metal-organic vapor phase epitaxy systems. So epitaxy means growing a crystal upon another crystal so that the crystal structure is maintained. This is a gas flow system with hydrogen or nitrogen. These are big systems, 2 meters in height, several meters in length. And with these tools, we can build layers upon the substrate surface. And here is a photograph of the newest reactor showing 6 sapphire wafers. These are 2-inch wafers there. So for a really big area, we can grow layers with a layer thickness control of less than 1 nanometer, and at the same time control composition and doping. And by building these layer structures, we can produce different devices. And one run in this kind of reactor produces about 100,000 LED components. Then a little survey on the applications where you see optoelectronic compound devices. So the internet is mostly based on optical fibers and sending light, sending information through these fibers. So there are diode lasers at the sending end, sending the light into the fiber. It's amplified on the way, and then at the end there is a photodetector. So optoelectronic components operate the whole system. And this chart shows the submarine optical fibers. So there are quite a lot of them, and this is really the key of how internet operates. Then everybody must have, at least in a computer or at home, one of these or several of these CD players, DVD players, and nowadays also Blu-ray disc players. So the optical storage density is increasing by using shorter wavelength and packing the information into a smaller area. In the last years, LEDs have been very forthcoming, finding new applications, mainly because of this gallium nitride technology. There are cell phone backlighting, LED TVs, even cars are starting to have LED lighting. Traffic lights have been for a long time being made from LEDs. Even street lights, general lighting is coming to the world of LEDs. LED efficiency has been growing really fast during the last 10 years. And actually the efficiency is approaching the theoretical limit of this phosphor-based technology, which means that we have a blue UV emitting diode with a phosphor material that converts part of the light into other parts of the spectrum so that it appears white to human eye. So the limit is a little bit over this scale here. So we are really trying to find new ways how to make this even more efficient. And with these technologies also the best solar cells can be made by having for each color of light a different junction to absorb that light, and the latest world records are around 44%. These kind of multi-junction solar cells are used in space and in concentrator, where you concentrate sunlight with mirrors into these supercells. Okay, and then I have two slides about current research and current directions, what we are doing. And one direction is to go into nano world in the active part of the optoelectronic device. So here is an example of nanowire forest, periodic array, not random array of nanowires. And the potential of this technology is that not increase in efficiency, but you consume a lot of less material, so savings in materials costs are huge. And we have also developed a new way how to pump these surface structures with a novel electronic injection. Another direction is to find biomedical applications for these devices. So we have made microarray LEDs, so very small LED systems. And here's a photograph of our LED inside a contact lens that is operating. So this is a photograph. And this is the artist's view how it could be used, for instance, to measure blood sugar level and give a signal if something is wrong. And we are also developing spectroscopic techniques to study the structure of cells. So thank you for your attention.